Hello and good evening, everyone. Welcome to York Observatory's TeleTube, the online astronomy and astrophysics program written and presented by the students, faculty, alumni, and friends of York University. We are broadcasting live from the Alani Carswell Observatory, located at York University in Toronto, Ontario, Canada. TeleTube broadcasts every Wednesday night at 7:30 p.m. local Toronto time. For any questions or comments you have about past shows, or if you have suggestions for future topics, please send us an email at observe@yorku.ca. You can also connect with us on Twitter or Instagram with the handle at York Observatory and on Facebook at Alani Carswell Obs. I'm Gagan, and I'll be one of your hosts this evening, along with Anita, Kat, Matt, and Prayosha. We are also joined today by Dr. Hyde and York University's very own Claire David as our special guest speaker. Tonight, we've got a great presentation about the exciting discovery of the Higgs boson at the Large Hadron Collider. Before we get started with our show, we'd like to give you a little update on what you can see stargazing this coming week. In the southwest sky, Mars is visible in the early evening, as well as the constellations Orion and Taurus in the south. Keep an eye out for the Orion Nebula, located under Orion's belt, as well as the Hyades star cluster, including the bright red star Aldebaran that acts as the bullseye in Taurus. The Pleiades, or the Seven Sisters, are also visible to the right of Taurus. Mars and the Pleiades actually appear very close together in today's evening sky. The constellation Cassiopeia and the Andromeda Galaxy are also visible lower in the western sky, and keep an eye out for the double cluster in Perseus. Try and spot these constellations if you get a chance to stargaze. A pair of binoculars or a small telescope are also excellent options to see some of the deeper space objects, such as clusters or nebulae. Let us know what you can see in the chat below. Now, without further ado, I'll pass the mic over to Professor Hyde to introduce our speaker for tonight.
Thank you very much, Gagan. That is an excellent introduction. And of course, our starry night sky has all kinds of dark spaces in it, maybe reminding us a little bit of the things we cannot see. And I'm very, very happy to be able to introduce our speaker. We have with us tonight Professor Claire David, one of my colleagues at York University at the Physics and Astronomy Department. Now, Claire's first degree was a Master of Engineering in Applied Physics at INSA Toulouse in France, specializing in nanophysics and instrumentation. During an internship on her 5th year at Triumphant in Vancouver, she was offered the opportunity to switch gears towards more fundamental science. In 2016, she obtained a PhD in experimental physics, or experimental particle physics, I should say, from the University of Victoria, working in the ATLAS collaboration, which I'm sure we're going to hear a little bit more about. She has continued working with ATLAS as a postdoctoral fellow at DESY in Germany, or DESY. I'm not sure if you pronounce it DESY. So since 2019, she is an assistant professor at York University, jointly appointed as an associate scientist at Fermilab, the U.S. National Laboratory near Chicago, Illinois. Her research on the subatomic world is split between the collider physics ATLAS, as mentioned before, and LHC, and in neutrino physics. She is starting the new Canadian effort towards the future Deep Underground Neutrino Experiment, or DUNE. So DUNE fans, make sure to wave in chat if you're here. And of course, hosted by Fermilab. She actually just started up a new webpage on York's science department, so yorku.ca/science/Claire David, if you want to see even more. So go ahead and take it away, Claire. We'll just get you to unmute here, and you'll be able to start sharing your slides.
Hello, I think that you can hear me, and soon you will be able to see my slides, I think.
Yes, we can see them great. It looks amazing. Thanks, Claire.
Thank you. Good evening, everyone. Thank you very much for the observatory to invite me. I'm very happy to talk about this fantastic story that is the Higgs boson discovery at the Large Hadron Collider. To start with, what is the Higgs boson? Why is it important? Why is this particle very special for particle physicists? Well, I'm going to answer all of these questions during this talk, but as this is an astronomical YouTube channel, let's just first start with this picture of the sky that some of you may be familiar with, where you can see galaxies, you can see stars, you can see planets. This is a lot of matter, and this is also energy. And if astronomers are looking at the skies through their favorite toy, that is telescopes, as you can see here, particle physicists are having different types of instruments. They use particle colliders, particle accelerators, and particle detectors. So let me relieve you. This image is a bit of a joke. We will never leave the Large Hadron Collider unattended, and it is not in the cafeteria at CERN. This is actually underground to be able to be protected from the normal day-to-day life radiations we get from outside the atmosphere. But these are our nice toys and tools, and this is how we investigate matter and energy through these tools. So particle physicists are doing the same as astronomers. They try to understand the universe, and then what differs is the scale. If astronomers are going to the very, very vast and enormous cosmos, the particle physicists are looking at the tiny. We are looking at the tiniest constituents of matter, which are the elementary particles. Seeing it in another way, we are playing Lego. This is not a joke. This is a very nice Lego model of the Atlas detector for educational purposes, and that keeps some of us busy to build it. But don't worry, we also work on the real thing for sure, and quite a lot of work, because that detector, as you can see in it here, under construction, is enormous. You can see some humans. One is here, another one is here, another one is here, and of course, one is there. So that was me, freshly landed at CERN in 2012 when I was starting my year of service there, taking some duty on call on the experiment while it was taking data that later served as to discover the Higgs boson. So I was at CERN there, and to see the detector not under construction like in that picture, but finished. This is a schematic that explains a bit how the entire machinery is there, with different sub-detectors that are there to be able to basically take pictures of particles collisions. We are going to see it soon with the video. So in here, the people definitely never have the right to climb on here. This is way too dangerous, but at least it gives you an idea of the scale. This detector is enormous. This is a 5-story building packed with electronics. That is a gigantic camera. Okay, back to our Lego box. It's important to know what we know first and where the Higgs boson is entering inside that story. So if you look at all the matters around you, you have two types of elementary constituents in the universe. You have what we call the matter particle, the technical name is fermions, and what we call the force messengers, the boson. So fermions are like the bricks of matter, and the bosons are like the glue, are like the messengers that are being exchanged between particles of matters. And it turns out that we are not having so many particles that are really in the Lego box of the universe. They're all combined to make all the elements. And so we are having the electrons that you can see in here, the neutrinos. This is a ghost image of the electron. And then we are having the constituents of the protons and neutrons that we call the quarks. And with all of these, you can make a recipe and combine them together to make atoms and all the elements that you know, that you see, and that you're also made of your own body. There are other generations of particles. We call them generations, and I symbolize them in upper shells because they are heavier and they tend to decay. They don't live long. They're created and then poof, they decay into the different other particles that you can see at the bottom. So this is why these particles are not so much familiar to you, because their lifetime is extremely short. On the other side, on the side of our force messengers, you may be familiar with electromagnetism and the electronics. And so for the particle carrier that is being exchanged during electromagnetic processes are the photons. So you know it with photonic photographs. And so these are grains of light that can travel at the speed of light very fast, and they're being exchanged during all electromagnetic processes. The W plus W minus Z zeros are the three dudes responsible for a lot of radioactivity processes. And this is part of what we call the weak interaction. This is one of the other fundamental forces. A third fundamental force is called the strong interaction, and the gluons responsible for them or as their name indicates, they are the glue that are binding the quarks together so that matter doesn't fall apart and all the atoms and the elements are just keeping their structure. So this is really super strong glue at the very, very tiny scale. And this is what holds matter together. Gravity is not part of subatomic physics. Einstein tried and he struggled. He didn't merit this. So the subatomic physics and our Lego box is describing all these particles of matter and then these three interaction forces with their messengers. So far, so good. But there's a problem. The problem is that if you take one particle, let's say the electrons, and you say it's as heavy as 2 apples. Okay, for comparison. The real masses are much smaller, but let's just put this comparison. Then the up quark will be as heavy as a laptop. Lift your laptop. This is not 2 apples, right? And crazy, but the top quark, all of these particles are volumeless. These are infinitely small entities. And the top quark will be actually having a mass that is corresponding to an aircraft in this comparison. Physicists are puzzled by the idea of why entities that have no volumes and just their types are different, why do they have a range of masses that is so big? So that was the first problem. And then there is something slightly more worrisome, is that in the theory and in the calculation, the way it's been built so far, at least until 2012, every particle is predicted to have absolutely zero mass. So on one hand, we have the theory telling that all the particles of our universe, they are not massive at all, none of them. And we see in experiment these particles, we've discovered them and we write down their masses and they're all different and we don't understand why in reality particles have mass. So the theorists are starting to ask this question back in the day, what gives elementary particles their masses? And this is where the Higgs comes into play. The Higgs boson is a particularity of what we call generally the Higgs field. So I have to introduce to you what is a concept of field is in subatomic physics. We use it a lot. So it's not a cornfield or no, it is actually something you have to think of way to parameterize the space. Space is being parameterized and finding this parameterization is our job as particle physicists to understand the universe. What are the knobs of our cosmos, right? And this is a comparison to introduce to you this concept, a very abstract of field in subatomic physics. You have seen the weather forecast and you know that even only the cities are being given the prediction of temperature. You know that between cities and in every point at the surface of the globe, there is a given value for the particle if you arrive there and you measure it. Right? And you can extrapolate to the entire universe. At every single point of the universe, there is a temperature. So we can have this concept of a temperature field. There are other examples that you can see. For example, the moisture, how it is moist in different parts in Sarah or in Canada or in Vancouver. And you can pick up a point at every single location of our cosmos. You can calculate, you can measure the moisture. So that's the concept of field. It's a way, how is your universe parameterized? And the Higgs field could be seen in this analogy with a field of snow. That's really handy to be able to explain the Higgs boson role and how it gives masses. So if you have a field of snow and a skier is going nearby, you will see that the skier is barely going to interact with the snow thanks to its very narrow skis, and it's going to be fast and it's not going to be slowed down by the motion. However, if you go for snowshoe hiking, you will interact more with the snow because of the snowshoes being very large, and then you will not be as fast as a skier. If you forget your snowshoes, like these women, you will sink inside the snow at the knee level and you will be very slow. So you can see in here 3 characters, 3 different activities. Depending on the interaction with the snow, we have a different speed. Or say differently, the more there is interaction with the snow, the more there is resistance to motion. And at the subatomic level, the concept of mass, we cannot say it's more matter, it's less matter, I remove. No, the completely basic element of our universe, the way to explain how some of them are massive and some of them are much lighter or massless is this idea of the Higgs field interacting more or less with these particles. So in here, a skier will be a very light particle, and this person with no snowshoes will be a very massive particle because her motion is being slowed down. Then you may wonder, what is then the Higgs boson? The Higgs boson is what we call in our jargon a manifestation of the field. If you create enough energy at a given point, then you will basically condensate your field of snow and you will form what's called a Higgs boson. In this analogy, a snowball. It is possible to see an entity of this Higgs field that is filled in everywhere in our universe by having locally a higher amount of energy, and then we will make a snowball, and that is how we can have a Higgs boson. So these the people that came up with this idea of telling, okay, there is a parameterization in our universe that is called the Higgs field, and if it exists, we will have a new particle called the Higgs boson, and that will explain how particles are in our Lego box are having masses. Of course, there's Peter Higgs, and he gave the name to that particle. So you can see him young, and then you can see him slightly later giving an autograph on the same Atlas Lego model that I told you before. As I told you, physicists are playing Lego. There are other people that I need to credit for the theoretical aspect of having gotten that idea at the same time: François Englert and Robert Brout, as well as Tom Kibble, Gerald Garanik, and Carl Hagen. These people gave this idea that we have in our universe the Higgs field, and it is the mechanism responsible of giving mass to particles. And that was in 1964. In 1964, a bit of historical context, we had Mary Poppins, we had the Beatles, and the computing infrastructure was not so advanced. And of course, these theories wanted to know if the Higgs boson exists or not, but it took quite some time, 1964, 2012, to be able to discover it. And this is where the story starts on how can we find the Higgs boson. So, as I told you, to make a Higgs boson, to make our snowball, we need to condensate our Higgs field. We need to create, in a given location of our universe, a high amount of energy. We need energy. And we need quite a lot of energy in a given tiny volume. And this is the only equation of that presentation, but I'm sure that you've heard of it. It's the very, very famous equation from Albert Einstein that found this equivalence between energy, that's the E, and mass, that's the M, and c squared is the speed of light multiplied by itself. It's the constant. And through this equation, what we should understand is that at the nuclear level, if you have mass, you can turn it into energy. And if you have energy, you can turn it into mass. And this is what's being done at the Large Hadron Collider. You can see the Large Hadron Collider has a sophisticated version, very sophisticated version of a hammer that is smashing particles to be able to locally have an enormous amount of energy. This is where mass turns into energy. And then when this will be this pure energy on a given small volume of our universe, new mass will appear, particles will be created, and this is where you can have a very nice smoothies of new particles and hopefully a Higgs boson. Here is your guide, the Large Hadron Collider. It took quite some years to write it on paper, what was this gigantic project, and then build it. It is a tunnel that is located between Switzerland and France near Geneva. You can see here Geneva Airport, and it is 27 kilometers of circumference. In this tunnel that is located 100 meters underground, there are these big pipes going that's inside or having a lot of magnets and dipoles and mechanism to be able to accelerate charged particles. And they accelerate charged particles in one direction, and there is another beam of particle accelerated as well in the other directions. And once these particles are reaching a speed that is 99.999999% of the speed of light, these beams are crossing and the particles can collide at specific locations that you can see here along the rings that are locations where we have particle detectors. And here is a video that shows a picture of the collisions and how these particles are going to be accelerated in the LHC and then collide.
Thanks very much. I'll just get that video loaded for you now while we're going. Maybe we have time for a quick question. Kat, do you want to go ahead and give your first question to the speaker while I transfer the video over?
Sure thing. Let's see. Okay, so what was an integral part of your research that led to some complications?
An integral part of my research that led to complication. I would say that there are lots of complications in research in fundamental science. It never really goes the way that you want, but perhaps when I was trying to optimize my analysis to be able to see better, I was realizing that there weren't many things to be done. So I had to be creative and I have to find other ideas and experiment what no one had tried before. So I can go back to it later after the talk if you want a bit more details. But it was a dead end. And in the end, I found out a way to be able to optimize in a non-explored area. So it was about exploring and trying to be creative in these explorations while looking at the data. I hope it replies to your question.
I think
Certainly,
it's great.
yes.
Yeah, it's a great answer, and it's good to emphasize as well the creativity you had to use there. All right, so let me go ahead and get this started for you. A video should be going now.
Okay, so in here we are actually inside the LHC, and we just passed the borders, and we are now going to be seeing a proton. This is a proton being accelerated with 3 quarks jiggling in here. And this proton is approaching the Atlas detector, and it's going to meet another proton, and they are going to collide at the center of the detector. Bam! Here it is, the collision, and mass is being created, and you can see all particles being produced. And the point of the detector as a camera for collision is to make a nice pictures of all the tracks created and identify the particles that are produced for each collisions. So I am going back to my presentation that you can see. Confirmation, Elena, if it's all real?
Yeah, it looks great. I can see your how can we see a Higgs boson? So it looks like you're good to go.
Yeah, that's the key questions, right? Because we built the Large Hadron Collider, we built this very sophisticated detectors. We have a nice image of a collision, as you just saw in this video. And where is the Higgs boson, right? Okay, sorry to disappoint you, but we can't see the Higgs boson in here. Okay, we can't see it directly. And I'm going to teach you how we, experimental particle physicists, analyzing the data from detectors, manage to see the Higgs boson. So back to our analogy of the snowball. You've been playing in the snow, I bet, during the winter, and you realize that the snowball is not something that holds forever. It can melt, or if you just fall, it just goes back into your field of snow. It decays, or it can be split into some parts, but this is not something stable. The Higgs boson is similar. In the theory, the Higgs boson decays. It doesn't live long. So we are going to focus on the Higgs boson decaying in 2 grains of light, 2 photons. That is a scenario that we'll consider, and this is a scenario where we could see actually indirectly our Mr. Higgs boson. So this is what is happening. We can have some collisions where the detector has identified 2 photons coming outside of a very messy collision that you've seen before in the video. There are many other particles, but 2 photons are identified. And then we can ask, okay, how can we know that these 2 photons are coming from a Higgs boson? Again, we can't know directly, but we have some tricks. Let me teach you the tricks. The first trick is that as the Higgs boson is produced so rarely, remember, we really have to get some high energy to be able to make one. We need an enormous amount of collisions. The Atlas detector is taking dozens of millions of collisions every second. And think of it as an enormous pile, and then we look at each collision. Of course, we have programs doing it automatically. We look at each collision, and then we ask, okay, are there two photons or not? If we have two photons, we keep the collision. If not, we recycle. It's going there for other people that wants to study other things. Okay, fine. Now we have our collisions having two photons. Great. What we do is that from this picture, we get a number. What number? Something important. See these two photons. We are going to add the photon momenta. Momenta could be seen as this arrow. It's a direction and it's a length. The direction means the direction of the particle when the particle was produced, and the length is linked to its energy or mass. It's equivalent. And what we do is that we sum these two arrows into a resulting arrows that is pictured in orange here. And this characterizes the energy of our two photon system. Our two photon pairs are being characterized with these arrows whose length matches the energy or the mass of that system. So in our language, we call it m gamma gamma. That is the variable that we have to compute this mass of a given two photons. We do this for every collision. And there are different cases. Either our photons are produced with small energy, so we'll have a small arrow, so a small gamma, m gamma gamma, or we will have very energetic photons taking almost all the energy of the collisions and not so much for the other particles created. That will happen rarely. And then we have a big m gamma gamma. And in the middle, we will have actually our Higgs boson decaying. Sometimes photons can be produced randomly, but sometimes this is the Higgs boson at a given energy, its mass that is going to decay, and then we will have these arrows. And the trick in here is that when the Higgs boson decays, it basically gives its mass as a trace of that decay. And the arrow that we compute with this calculation matches actually the energy, the mass of the Higgs boson itself. So if there is a Higgs boson, we should actually see more collisions that are having this specific arrow length. In the theory, we could not guess in advance what would be the Higgs mass. So what we do is that we find a way to see all these collisions at once to try to see where the Higgs could lie. And this is a little animation that shows you actually that from the given ranges of our m gamma gamma, remember that length of arrows that characterize of photon pair energy, we are going to count the number of collisions. So we count, that's what we do for a living. We have different collisions, and we put them into this graph depending on where the length of the arrows are. So you see for a small little arrow that will go on the left of the plot, and this will happen often because it's easy. Nature is lazy. It's going to produce a lot of very lazy photons. But at some point, it's going to have very energetic photons resulting in a big orange arrow. And we do this, and we realize after a while that we have what we call a falling background. Most of the collisions, remember, the Higgs boson is rarely produced. So most of boring, uninteresting collisions are having the strands of a descending staircase or a slope, as you can see in blue. Now, if there is a Higgs boson, we will have specific value of our arrow. For example, we'll have more collisions in the second column. And that will mean that on the plot, we will see a bump. And this is why the people looking for the Higgs boson were actually called the bump hunter, because definitely they were trying to find a bump through the data. And here we go. I prepared you to see the real plot. This is my challenge for tonight. I want you to understand what are the real plots that was behind the discovery of the Higgs boson. And for this, we will not see the picture of each collisions. This is going to vanish. And in case you will see actually a dot that matches for this specific energy or mass of m gamma gamma, we have this number of collisions. And as we take a lot of collisions, prepare yourself to see a lot of a high number. So here's that plot. You can see here, this is our blue background, and we have many, many collisions coming in. Of course, here it's more narrow. And all of these black dots are the number of data. You see the dates is just advancing. And here we have up to 4,000 collisions at a very little arrow. And if we see a bit, oh, look at this. There is here a bump. There is a bump. We can see it better on this graph at the bottom, which is the same as above, but we've been subtracting the blue slope. We've been flattening the curve sort of to only let the bump appear more clearly. And this is here. You can see that we have actually way more collisions that are for the specific value of m gamma gamma. And it turns out, after a lot of checks and a lot of cares and a lot of several studies that were for months to be really, really sure of what was this bump about, it turns out that this was completely consistent with the prediction back in 1964 of the Higgs boson. So here we go. We completed our Lego box by having our same bricks as before, and also the force messenger, but we have Mr. Higgs boson that is added to this box, and that explain why particles are having masses and other particles don't, thanks to a very tweaked interaction between these particles. The Higgs is the molas of the subatomic physics universe stew, and it explains what is mass at the subatomic level, because before 2012 we really didn't know. And that was quite a celebration. You can see the lineup of so many students and physicists. I was at CERN back then, and I could not enter the room because you had basically to camp the day before at 10 p.m. to be able to have a chance to enter. All of the most important people were there, the people that were so crucial in this entire endeavors, as well as very enthusiastic summer students at the back of the room that were cheering up everyone. And Peter Higgs was there, and he was pretty emotional because, as he said, it's really an incredible thing that has happened in my lifetime. He was having this idea back in 1964, and it took 48 years to be able to discover it finally. So what a relief for him. He got, along with Francois Englert, the Nobel Prize of Physics in 2013. So that marked quite a big achievement, the biggest achievement of the Large Hadron Collider, the discovery of the Higgs boson. We were really happy. We celebrated a lot. I was starting my PhD thesis at that time, and my thesis was having a Higgs inside the scenario that I was studying. So I was relieved myself as well. But of course, this is marvelous to have had so many technological challenges to be able to build a very complex machine and be able to claim that endeavor and that achievement. And you may wonder, okay, are we now at the beach and doing nothing? Well, actually, this is not the end. The Higgs boson discovery is the beginning of a new area in physics. It is actually called Higgs physics. And the Higgs boson is now used in so many analyses and in so many studies to be able to understand more our universe through its tiniest constituents. The Higgs is used at what we call a portal for dark matter searches. We are searching for dark matter particles that will be produced when the Higgs decays. It's not the Higgs decaying into photons, it's the Higgs decaying into dark matter. There are people studying this right now at the Large Hadron Collider. And of course, the Higgs can decay into particles we have absolutely no idea about, new particles that are yet to be discovered to be able to complete our Lego box of the universe. So the game is not ending, it's actually a continued quest forever. And at least in 2022, the Large Hadron Collider is going to start again, taking data. And the plan, what we have at the menu, is to study more the Higgs boson. We haven't really finished to take all of its mensurations and properties. And we are definitely looking for dark matter. This is a very big enigma in physics today. And of course, we can discover new particle and we can have a complete surprise. This is the excitement that we have as particle physicists when we explore at colliders at what we call the energy frontier. So this is the Lego box of the universe that keeps particle physicists busy trying to solve the mysteries about matter and energy. I hope you enjoyed this talk, and I'm very happy to answer to your questions.
Thanks very much, Claire. It is great to have you on. Of course, we have all kinds of questions from YouTube and our crew, but I believe, Matt, you are up first with your question.
Yeah, actually, taking into account what you just mentioned, my question was that what does the discovery of the Higgs boson mean to you and your ideas for new research projects, like personally?
Personally, thanks for precising, because for the field it was enormous.
Yeah.
For me, I was very biased because when I arrived in 2012, I was barely starting my PhD thesis. So I was really in need to ramp up to understand what's going on, how to code, and start my own project. But my own project involved a Higgs boson inside, as I say, inside the analysis that I was assigned to do. So I was actually very relieved that the Higgs boson was discovered, that we knew the mass. So how it changed the deal for me very specifically, it was that before we didn't know what the mass of the Higgs boson was. So I had to be able to anticipate several possible values of the mass. And after it says, okay, it's 125, good. So actually my code and my program and my research simplified a bit, but then it got quite complicated after some time. Later on, when I was no more a PhD student, but a postdoc, I was involved into another big endeavor of the Large Hadron Collider, very rare production of the Higgs boson. The Higgs boson can be produced by energy, as I said, but there are different ways of producing it when a collision occurs. And there was actually a way that was not discovered yet. It's the Higgs boson produced with two quarks, a top and an antitop. That was the scenario that was looked for, and I was part of a team, and we produced a paper that was the first observation of that very rare production mode of the Higgs boson. So I continued studying the Higgs boson. Right now at York University, I switched gears and I am in a group on the Large Hadron Collider and on the ATLAS collaboration that is called Exotics, and these are very specific scenarios that some theorists are coming up to be able to explain what we still don't understand in the model. And these exotic particles are produced by the decay of the Higgs boson again. In the analysis, there is, in all of the decay chain, from the collisions to the particles we want to look for, there is the Higgs boson in the process. It happens in a lot of analyses. The Higgs boson is pretty much the superstar at the moment because there is a high potential to be able to find new things that we are eager to know about subatomic physics.
Excellent, wonderful, and it does actually go very well with a question that just popped up in the YouTube chat. I think you've talked about this a bit already, but one of our guests over live now asked about ways to minimize the error with collisions. Is taking these different types of measurements one of those ways you might consider?
These errors of collisions, that could be very vague. There are so many different errors, and so if the person can rephrase, I can perhaps answer more the question of this person. But what I can say is that we have many different ways of making errors. There are some errors of alignment. So when we are making some collisions, it's not only one particle colliding, it's 1,000 billions of particles on one side and 1,000 billions of particles on the other side. And they collide, and some of them are passing through, and others are just really colliding hardly, and this is what we have of interest. So there are detectors small detectors before we enter into ATLAS that are checking if things are correctly aligned so that at least the collision happen very nicely and we do not have so many misses. So that's one type of errors that we minimize this way. Then the ATLAS detector is a very fancy camera, but the job is quite harsh. Is to take, right now it takes 40 million pictures per second of high definition collisions and trying to reconstruct all of the tracks of the particles and identify them. Here, the key thing to avoid a lot of mistakes is to do calibration. So we take a lot of collisions of processes that we know, and as we know these processes, we can see how, let's say, an electron in the detector is going to be reconstructed. If we know that two electrons are produced having a specific arrow, as I told you, that corresponds to a particle we know, for example, the Z. The Z boson is decaying into two electrons, and we know exactly how these two electrons are going to have as a resulting arrows in their energies. So then what we do is that we study how an electron is reconstructed, if it has some errors into its energy, etc. So we do a lot of calibrations, and we refined our programs and our code to be able to calibrate better and better. And through this effort of calibration, then once we really do the physics, we are ready to be able to have collisions that are correctly taken by our detector.
Wonderful. And let's go ahead and take another question, this time from Anita. Can you go ahead and ask one of your questions?
Thank you. So I was wondering, is there any chance that Higgs boson particles explain dark matter?
There is a chance, to be honest, we don't know this, but this is what we search. There is a chance that the Higgs boson can be what we call in our jargon the portal, or an open door for dark matter, because it could be, as it's quite heavy, it's going to decay into different other particles, and it could be producing dark matter particles. And dark matter is a type of matter that is non-visible, hence the name, but we have no idea what it is. We just label it dark matter, but we have no clue. However, we know that it's there through astronomical observations, actually. This is why some astronomers listening here right now can be interested. This dark matter, as it's barely interacting with the regular matter, what it's being done is that it's not going to leave any trace in the detector. But we have still a way to be able to detect it indirectly again. If at some point you have a ball of paintball, or a ball of paint, or a balloon that is just filled with colored water, and you let it fall on the floor, what you can see on the floor is just an explosion a bit in all directions, right? It will just balance itself. If there is a stain this way, there is going to be a stain this way, and it's going to be balanced, right? The energy is going to be conserved in all directions after the shock. Sometimes in the detector, we have some collisions where all of the particles are on one side, nothing on the other side. It's completely imbalanced. And in these events, we compute actually from all of the energy or mass that is just produced in one direction, we compute what is not produced in the other direction, and we call it the missing energy. And when we do computation with the missing energy, we can have a clue if actually behind it, we have either a complete miss, the detector not having reconstructed regular matter, or if we actually have the presence of dark matter that went there, escaped the detector, and was not detected because our regular matter is not meant to detect it yet. We don't know. So that's a possibility to detect at the Large Hadron Collider dark matter, and we use the Higgs boson as a way to be able to potentially find it.
Wonderful. And we're all, of course, all of us astronomers over here looking forward to this discovery. Now, Gagan, you've also got a question for our speaker today.
Yeah. So, in your opinion, how can the discovery of the Higgs boson affect the future research in physics and astronomy? And this is a bit of a more general question, sort of in relation to Matt's question. So, what are the implications of the discovery on the field?
Oh, it can affect it in many ways, but I would say a way that it affected it's first, it makes us understand. I will stop here for a second. We are Homo sapiens, we are curious, and all of our accomplishment as a species is because we want to know. So we wanted to know how the mass works at the subatomic level, and the Higgs boson gives elements of answer. There are still new questions being created, but at least we got that understanding. So this is a huge accomplishment in terms of knowledge, for sure. Then some people, utilitarian people, says, what is it for? Well, when Michael Faraday was presenting at the Royal Society of London his work on electricity and magnetism, people could see a little thing stirring with the action of a magnet, and then he invented the dynamo. But then people were saying, what is it for? What I can say is that the Higgs boson discovery, apart from filling the gap, being the last pieces that were missing, and the discovery confirming an excellent theoretical idea. Apart from that, perhaps ask your question in 200 years, and then we will see how this discovery will later on revolutionize the world. At the Large Hadron Collider, there's been many spin-off, many inventions on the side, not really what we wanted, just doing this adventure of the Higgs boson discovery got physicists to invent the internet to communicate better. And then some people came in and says, this particle detector, what if we put a human and we make it safe? Perhaps we can see inside a human. Medical physics was born. So the field is so innovative, it's so hard, so we have to push the frontier of technology that we innovate along the way, and that is transforming our society. I don't think you can imagine how was the world before internet. This has completely changed our day-to-day life, so it is going to have some impact, definitely, for everyone.
Indeed, and we're currently using the internet to broadcast this, so it's very appropriate. Now, we have just a bit more time left for today's broadcast. Prayosha, why don't you go ahead with your question? It's a good round off question for our speaker.
Yes, my question is, what inspired you to become a physicist?
That's a very nice question. So yeah, I didn't want to become a physicist at the start. I was basically, I think I wanted to become a car designer when I was very young, when I was 15. And then I was very curious, well, not curious actually, I was uncomfortable. So the first element of answer that I can bring to you is I was uncomfortable because I had many questions about my classes in science and math, and I was about to stop asking questions until at some point I was sent into a scientific camp over the summer. And I met people my age that were actually reading Stephen Hawking and doing math riddles until 3 a.m. So I realized actually that we could have a passion like horse riding, soccer, but that's actually what we learn at school. So I quickly became fan of the particle detectors because I found this machine fascinating, like so huge to detect the very small. And I did an engineering degree first, but this is actually during an internship that I saw a very nice graph, very colorful. And I asked the particle physicist, hey, how from the data of the detector do you make that graph? And he was busy and he was telling me, oh, you have to do a PhD for that. And so I embarked on the adventure of a PhD, not really much for a career, but to answer my own questions. How do we get from the data towards a plot, a graph, and the answer? Like, how do we understand the universe better? And while just starting this PhD, I got the answer to my questions, but I got many more questions and I found it even more interesting. So here we go. I became a particle physicist.
That's wonderful. And I think we have time. There's one question that goes really well with this. Kat, do you want to go ahead and ask your second question?
Yes, sure thing. So what is some advice that you'd give to an aspiring physics major or physics specialist?
To a physics major, physics specialist, I would say don't forget to have fun. It can be very overwhelming, all these exams and the fact that we are judged during the academic career and path. So don't forget to have fun, and then listen to yourself. It sounds a bit cliche, but if you follow your interests, no matter how hard, it will bring you joy and it will basically fulfill you. And this is pretty much what I did. I was warned at some point, this is so tricky to become a physicist. Not so very few people are making it. And I was saying, okay. But I ignore it a bit and try to only focus on what I was interested in. So having fun, having some interest, trying to feed your own thirst of knowledge, this is the key to carry on. And then at some point, things are working on their own, because once you have an interest, once you have love in what you do, definitely opportunities are coming, and then you can see you at a place that a couple of years before you will have not imagined that you will reach there.
Wonderful. That is fabulous advice, and we should probably not keep you too late tonight. So we'll say thank you very much to Professor Claire David for joining us tonight for this fascinating talk. And we had a bunch of people very keen in on chat today, so it's been a great success. I'm just going to steal back your screen share here for our final little outro moments, and we'll go ahead and say, hope to have you back again soon, and can't wait to find out what all you end up finding out about dark matter, in particular, how it behaves and how, of course, us over on the observational side can use it. So I'm going to take a moment now and say, a big final thank you to Claire for joining us, and we will go ahead and hand over to Gagan for our outro. So, sorry, actually, Kat, you're doing the outro, aren't you?
I am, yes.
Take it away, Kat.
Awesome. Well, everyone, you have been listening to the Alan I. Carswell Observatory's weekly TeleTube broadcast, the Astronomy and Astrophysics program, written and presented by the students, faculty, alumni, and friends of York University. The hosts this evening have been Anita, Matt, Prayosha, Gagan, and myself, Kat. A special thanks to Claire David for joining us and delivering a wonderful talk. For more information on Claire and her research, please visit www.yorku.ca/science/Claire David. Make sure to leave any comments or questions in the comments section of the video below and talk to us in the chat right now. We will be around for the next 20 minutes or so to answer your questions. All of our programs are free, but if you would like to make a donation, see our website at observatory.info.yorku.ca. You can always connect with us on Twitter with the handle at York Observatory, and check out our website for show notes, content updates, and contact info at observatory.info.yorku.ca. Thanks for tuning in, clear skies, and have a good night.